702 and Cape Talk.
The Naked Scientist.
Dr. Chris Smith, good morning.
Good morning.
And how are you this Freedom Day?
Do you know, I didn't realise that so much time had passed. Isn't it wonderful that we're so far on?
24
I know,
years,
24
yeah.
years. Incredible. Almost as far down the line as DNA, which is celebrating this week its 65th birthday, since the famous paper published by James Watson and Francis Crick in the journal Nature, announcing what James Watson dubs the science of the secret of life.
So this week was World DNA Day. So what happens on World DNA Day? So we mark the anniversary of this paper. And what did the paper do for science? What did it do for us? What did it tell us?
Well, back in the day, in 1953, there's quite a famous story around this because James Watson and Francis Crick were working in Cambridge using information that they got from another scientist, Rosalind Franklin, she's unfortunately no longer with us, but she had managed to get some very precise pictures using X-rays of crystals of DNA. Using that information, their own insights and more data they had gathered, Watson and Crick managed to build a model of the structure of DNA. We knew that cells, almost all cells in the human body, for example, have this molecule in their centre. We knew it gets passed from one cell to its daughters, but we didn't have any idea really how it could encode a message or a recipe, because that's what DNA is. It's a recipe book that tells your cell how to make all the chemicals it needs to make you. But no one really understood how that could work. And then when Francis Crick and James Watson put this together and built this famous model, which actually showed how you could have a structure, this what we talk about, the double helix. So you've got two strands, one the mirror image of the other, where you've got these genetic letters, they're called bases, and there are 4 of them, A, C, T, and G, and they bind together in a very specific way, and they spell out genetic words. We call them genes. Those genes are the recipes. And so it really did show us how we had locked away in our cells the recipe for life and how this could be copied and also passed into future generations. So that was the first step, really. They had to then do a lot more work to work out exactly what the code was that was locked away in the DNA, but this was the first insight into how you had something that could do that. So it's pretty important because it has gone on to revolutionise the world. If you think in my field as a virologist, our microbiology laboratory now tells you in hours to minutes what an infection is, what the virus or the microorganism is, what drugs it's sensitive to, and therefore it informs all kinds of management, drug treatment, infection control. We couldn't do that before. Now we can. In literally hours we can have a person isolated on the right treatment and not infecting other people. Years ago we were trying to grow all these things, and basically we're very good at telling people 2 weeks later what they either died of or what they've recovered from. Now we've totally turned that around. And then we're doing forensics with this. People are even talking about storing information in DNA. So Massive Attack, the group, they're actually storing an album in DNA in Switzerland. So we're sort of pushing back the frontiers of what we can do with DNA, and it's really made a huge contribution. And in just 65 years, we've gone from not knowing how we passed on our genes from mother to child or father to child to now understanding enormous amounts about what makes the world tick and how evolution works.
So how do you go about storing an album in DNA?
Oh, it's clever, isn't it?
What's going to do this?
First of all, the premise is important, right? Why do they want to do this? Well, if you think about it, we can go to a Neanderthal skeleton, which scientists have done this. Neanderthals haven't been around on Earth for more than 20,000 years. We can extract DNA from the remains of that Neanderthal and read their genetic code. So we can see, even though these people, in inverted commas, have not walked on Earth for more than 20,000 years, we can still see the recipe that made that individual, because DNA is very robust and very resilient. So scientists are saying, right, okay, this is a much better storage mechanism than a CD. My computer won't play CDs that I wrote 10 years ago. They've already rotted away. So DNA can survive 20,000 years. It's also extremely compact. So what you do is you write a computer program that will convert whatever your data is into a DNA code. So it's not the same code that makes a human, but it's a way of taking a combination of 4 letters, A, C, T, and G, which is the genetic code, and writing data from a computer program into that DNA code. You then synthesize the piece of DNA, and there are loads of companies around who will do that. It's not very expensive anymore. And they send you a little test tube with some tiny flakes in it, which are the crystals of DNA, and that will sit there. until you want to read it again, and then you add some water, dilute it, copy the DNA a few billion times, and then you read the genetic code and you use the sequence of DNA, and then you use whatever code you used in the first place to turn your data into a combination of A, C, T's and G's, to read it back and recompile the original data. And people are doing that. I mean, there's a guy at the Sanger Institute where a third of the genome was decoded about 15 years ago, Steve Goldman and his group. They actually did this for one of the works of Shakespeare, a computer program and a nice picture, and they've shown that you can do this and the DNA will store the data for you, and it will do it reliably. So maybe this is one way that we could store a huge amount of the world's information in a very robust way. And there's an Armageddon scenario around this, because people are saying if the world, civilization, etc., decided to destroy itself tomorrow, it's very unlikely you'll find a DVD player or a hard disk knocking around when civilizations put themselves back together in a couple of hundred years' time. But they'll still be using DNA. So if we store all of our knowledge in DNA, the people who do come downstream of us will be motivated to read DNA anyway, because it will still be in them, it will be in all the plants and animals that are in the world around them. Therefore, they'll have developed techniques to read DNA, so they'll go and read our DNA and they'll work out what we'd stored for them. So it's a way of safeguarding our future.
I mean, it's been interesting. Like you say, in 65 years, we've gone from knowing very little to knowing a lot. But what are still the limits? I remember I was reading something for another show about how you respond to food or your eating habits, whether you like sweet or sour foods, can have a lot to do with what you would have inherited in genetics from your parents. And I think it spoke specifically about from your mother. So, I mean, how much do we still need to know? Because it feels as though, I mean, at some point, surely there's going to be a limit, or haven't we even begun to unpack what DNA tells us?
Well, when scientists like James Watson, Francis Crick came along and said, well, we've discovered the secret of life, they've only discovered the first inklings of the secret of life, because what we've since discovered is that there are 3 billion genetic letters in the average human. A fraction of those actually code for genes, which are the recipes that make proteins, which are the chemicals that make your cells work. But there's a huge amount of DNA, which we'd originally written off as junk. We thought it was just there like scenery. In fact, there are all these really important elements in there that control when the genes are on or off, or there are bits of DNA that don't turn into proteins in cells, but they do make bits of genetic information that do really important jobs in cells. So then we thought, that's it. We now understand things a lot better. And then along comes this whole idea of epigenetics, which is that it's not just the physical sequence of the DNA that makes a difference as to what your cells do. There are chemicals stuck onto the side of your DNA that control how strongly turned on or off different genes are. And that can be influenced by the environment, and also it can be inherited. So there's more and more layers of complexity being added all the time to this, and we're learning more all the time about this, and we realise how complicated and how difficult the task ahead of us to understand the world around us from a genetic perspective is. But at the same time, we're slowly developing incredible tools to do it. And just the other day, scientists invented a thing smaller than your average smartphone, which will now read the entire human genome in a matter of days. And what took a warehouse-sized building with thousands of machines in it, millions of person hours, and billions of dollars, and about 15 years, about 20 years ago, now takes a matter of hours on a device the size of a mobile phone, which is just incredible to do this. So technology is handing us the tools to understand a lot more, but there's still a long way to go, which is a good thing because it keeps scientists in business.
For now, let's go to Joburg, where we have Renata on the line. Renata, good morning.
Good morning. Good morning, guys. Good morning, Dr. Chris. It's honor to be speaking to you. I've got a very difficult question. I had a lot of operations in my life, and they healed so quickly, and it's unbelievable. And last year, I had an implant done, which was subsequently removed, and my nerve was damaged, and I'm in a severe, severe pain for 1 year and 3 months. Is there anything that can be done for me to not having this pain anymore?
Hi, Renata. I'm very sorry to hear that you're experiencing some difficulties. There's a range of reasons why, after surgery, a person can get severe pain. One of those reasons is because in doing the surgery, doctors inevitably end up doing damage to tissue, including nerve tissue, and sometimes that damage can be sufficiently severe that it reprograms the nervous system a bit in the area where you've done the intervention, and it can make inappropriate connections in the spinal cord, and this leads to a pain state which is called neuropathic pain. There are other instances why a person might suffer intractable pain, and it may well be that the operation hasn't been done very well. There may also have been a damage done when something was inserted or implanted, or something's pushing on something or impinging on something. It's certainly worth excluding that as a possibility as well. Another reason is that sometimes painkillers given to block pain at the time when the surgery is acute can sometimes trigger the spinal cord to rewire itself so that then pain becomes chronic, and opioids like morphine-like drugs can sometimes do this as well. It sounds to me that as well as seeking a careful opinion and reassessment from the person who did the surgery to make sure that there's not some structural reason why you're suffering severe pain, exclude that because that can be fixed. Exclude that first, and then you need to see a pain specialist, because if it's not a structural problem caused by something that could be fixed surgically, this could well be a neurological thing caused maybe as a consequence of the surgery or the drugs used in the surgery, and a pain specialist is very good at sorting out what's causing this and how to deal with it the best way, because there are various techniques that can be used, and in this modern era there's no reason for a person to suffer chronic intolerable pain. We're very good at managing pain these days, but you need to find an expert who can do that for you. Good luck.
I believe that the only solution for me is for this nerve to be destroyed in order not to feel pain. I would be numb on that side, but not feeling the pain. What is your solution to this?
Well, as I say, I'm not your doctor, and I haven't seen you personally, but I would go and see a pain specialist, because yes, we can destroy nerve tissue, which will block the flow of pain, but there are other less severe approaches that might work better first. And so you start with the simple things and you try those first, because the simple things also tend to be the cheaper things and the safer things, and you slowly escalate until you achieve a solution you're comfortable with.
Neuropathic pain is such an interesting one. And my mom recently had numerous surgeries, and one of the things they told her was sometimes it's just a matter of, so there isn't a site of pain, it's just because of the damage to the nerve. And sometimes it can't be fixed if the damage is too extensive. Even if I don't know what the actual process is called, but if you burn the nerve, you can't necessarily fix the fact that there is a pain signal in that particular place. So, what does that tell us about how we understand pain, this idea of neuropathic pain?
If you look in the spinal cord, there's a region of the spinal cord at each level up your body, which receives inputs from nerve cells which are pain nerves. And when they turn on, they tell your spinal cord that in that patch of the body, there's severe pain or damage going on. Further down inside the spinal cord is another region which responds very well to non-pain signals. It's a localization signal. It tells your spinal cord where on the surface of your body we're talking about. Now, when you have a severe injury or surgery and you damage a nerve, for some reason we don't really understand, if the damage to pain nerves causes them to die. But damage to the nerves that are much bigger, more robust probably, and signal fine touch and location on the skin, they don't die, they can regrow. And so one theory is that the surviving non-pain nerves grow back into the damaged or surgical area, but also in the spinal cord, where the pain fibres had connected and have now died off. It leaves cells feeling deprived of their inputs in that part of the spinal cord. And this releases signals that then tell the adjacent surviving incoming connections, connect to me. So what you end up with is the cells that would normally subserve fine touch and sort of stroking motions and location on the skin, which don't need a painful stimulus to drive them, they end up connecting to the pain centres in your spinal cord, so that things that would normally be a stroking or a tickling sensation, totally non-painful, ends up eliciting the sensation of pain in your spinal cord. And that's why you get this phenomenon of neuropathic pain. And it can be really hard to control, because you've somehow got to persuade the spinal cord to rewire itself, to unwire those incorrect connections and rewire the correct connections. And this is why painkillers can sometimes not be very effective in these settings, for the simple reason that there's not actually a pain stimulus there to abolish with a painkiller, because it's an inappropriate bunch of nerve connections that are doing this. But there are ways to block these signals. You don't necessarily have to cut nerves, but you can use electrical implants and other techniques to abolish the conduction of those impulses in the pain pathways from that part of the body, which can help bring relief to patients.
Lida in Germiston, good morning.
Hello.
Yes, Lida.
My question is, does the world have a birthday?
Aha, that's a very good question. Lida, how old are you?
I'm 8 years old.
Aha, and when is your birthday?
On the 18th of March.
18th of March. Okay. Dr. Chris, does the world have a birthday like Lida has a birthday on the 18th of March?
The answer is the Earth sort of does have a birthday in the same way that the universe has a birthday. The universe is the oldest, it's 13.8 billion years old, and the Earth, we think, was born or formed about 4,500 million or 4.5 billion years ago. So the Earth is pretty old too. And the Earth formed by dust and gas and other material forming in a disk around the young star that was going to become our sun. And slowly that disk of gas and dust aggregated to form baby planets called planetesimals, one of which was the Earth, and then under its own gravity it began to scoop up more of the gas and dust in that disk until you ended up with a planet-sized blob that we call the Earth. And added to that subsequently was another planet about the size of Mars collided with us about 4.5 billion years ago, and that gave us our moon. So our moon has a birthday as well. And about 4 billion years ago, loads of asteroids and comets rained in on the Earth from the forming solar system, and they brought lots more mass and lots of water. So a lot of the water we have on Earth came from outside. So the early Earth does have a birthday, the moon has a birthday, and our party that we had subsequently was when all the water arrived.
Lida, does that answer your question?
Yes.
Thank you so much for your call.
Thank you.
That's Lida in Germiston. 4.5 billion years is how old the Earth is. Gordon in Constantia, good morning.
Good morning to you and to Chris.
Yes.
I have two somewhat interrelated questions, I think. It's wonderful that we've had lovely rain here in Cape Town, and watching the rain running down a steep window pane, steeply sloped window pane, could be vertical, I've noticed that raindrops form little rivulets which tend to wobble from side to side in a meandering fashion. So that's part A. Part B, I run a few hives, and when I'm pouring honey from a big jar into smaller jars for giving to friends, I notice that the honey starts pouring out of a jar, a great big glob. As it speeds up, it thins to a thin stream, which then wobbles backwards and forwards in a meandering fashion. And I'm wondering why a viscous fluid would meander from left to right, whereas when you pour tea, water out of a kettle, hot water, a non-viscous fluid doesn't meander. Are the two related issues, Chris?
Hello. What a wonderful observation. Congratulations to you. I think you're probably right. I've never thought about this. I don't think I've seen the phenomenon, but I can imagine it happening. I'd have to go away and think about this. I mean, it's a fluid dynamics question, and it will be to do with the viscosity. And water is still viscous, and hot water will be less viscous than cold water, and that might be why the raindrops are doing it more than when you pour water from a kettle. You would be less likely to notice this. But I mean, I think the reason is the one you've identified, which is that you've got a viscous fluid there. It's very thick, and basically, as it starts to fall, then it's going to basically make itself easier for it to run over itself, because the fluid forms a sort of tube inside the fluid, a bit like a stalactite going down. And I suspect that there's going to be forces exerted where it meets the air, and there's therefore going to be some asymmetry in those forces, which is going to make it easier to move on one side, but then it feels more of a force from the other side, so it moves back, and it's going to sort of wobble to make its way down. With the window, it's probably a similar phenomenon, but it might also be hitting little obstructions or dirt on the window as it runs down, and so that's going to apply a small force, which is then going to make the water blob a little bit asymmetrical, which might push it in one direction, then back the other way. But it's a very interesting observation. I do know some fluid mechanics people. And I'm going to go and ask them if they've looked at this, because there's probably a really elegant mathematical equation to describe this. But I think you're right in your suggestion that this is because of the viscosity. But I will go and inquire, because it's a really, really fascinating observation, and thank you for highlighting it.
Can I build on that? And that, as an earth scientist, I understand that in a river that has a very low gradient, it will tend to meander. And the meandering fashion starts when the river starts a bend. On the outside of that bend, the water is then flowing at a much faster pace than on the inside, and therefore there's higher energy, and erosion occurs on the outside of a bend, whereas on the inside, the water then slows down and drops its load, so you build a bank from the inside towards the outside. And that's generally the principle of a meandering river formation. But here we're dealing with something that is subvertical, a window pane, so there's very little sense of resistance, I guess. And similarly, when you're pouring honey, there's very little resistance in air. But I'd look forward to your answer.
Thank you very much for
thank you
that.
very
That's
much.
Gordon in Constantia. Gibson in Pretoria, good morning.
Yes, good morning. My question is, why is the center of the Earth, the core, why is it remaining molten until today?
Hello, Gibson. The answer, well, there are several answers to this. One is that the Earth is a reasonably large planet and it was hot to start with. The second is that when the Earth formed, all of the material in the Earth was jumbled up with some really heavy stuff towards the surface and some lighter stuff deeper in. And under the effect of gravity, which pulls the heavier stuff downwards, then the heavy stuff, like iron, is going to make its way towards the core. And as it makes its way towards the core, it's going to rub frictionally against the lighter stuff, which is trying to be displaced upwards. So there's some frictional heating for that reason, and that generates some heat. But by and large, the largest source of heat within the Earth is that when it formed, it contained a large amount of radioactive elements, things like potassium-40, thorium, and others. As these decay, they give out radiogenic heat. The process of radioactive decay is heat-producing. So the Earth has some heat to start with. It's made some heat by the conversion of gravitational potential energy into kinetic energy, thermal energy, as the Earth has matured. And it's also continuously producing heat by the radioactive decay of chemicals which are locked away in the hot core. And that means the core is about 5,700 Kelvin, close to centigrade, it's 273 degrees different. And it's producing so much heat and losing heat only at a certain rate that it's cooling only very slowly. So even though it's 4.5 billion years old, it's still extremely hot in the centre.
Okay, thank you.
Thank you very much for your question. That's Gibson in Pretoria. And Dr. Smith, thank you very much for your time this week. Always a pleasure chatting to you.
Oh, thanks, Googs. See you soon, everybody. Bye-bye.